Welcome to Calculus.
After many years of combining like terms to make one expression, now we get to take it all apart.
On this episode, Stevenson will demonstrate
Here's another example of linearization. However, this time we're given a table of values. So this is the question stem, and then this is the particular part that is being asked of this question stem. Let's go through it. Let k be a function that is differentiable for all real numbers. The table above gives the values of k and its derivative k prime for selected values points x in the closed interval from -3 to +3. The second derivative of k has the property that k double prime is less than 0 on this closed interval. Okay. All right, so this is the question stem. So this is setting the scene of our problem. Now, what do they want us to do? Write an equation of the line tangent to the graph of k at the point where x equals -2, and then use this line to approximate the value of k evaluated at -2.2. Is this approximation greater than or less than the actual value of k evaluated at -2.2? Give a reason for your answer. Let's think about this. What do we have to do? Well, the first thing we need to do is find the equation of the line tangent to our graph of k at x equals -2. We're going to use the table of values to do that. Once we have that equation, then we're going to use it to approximate this value of k evaluated at -2.2. That's the linearization idea. And then we have to answer this question on whether or not it's greater than or less than the actual function evaluated there. So we'll come back to that. So there's three parts. So first, let's come up with the equation of the tangent line. So remember, what do we need? A point and a slope. Well, let's look at our table. The point, we're looking at x equals -2. So we come up here and we realize we're looking at -2. So what's the ordered pair? Well, when -2 goes in, what does k pop out? 2. Now we need the slope at this point also. The slope at -2, k prime, is 7. Now we take these two pieces and write the equation of our tangent line. We've done the first part. We found the equation of the line tangent. Now what are we going to do with it? We're going to use it to approximate the value of k at -2.2. So I'm going to take the -2.2 and I'm going to plug it into my linearization of k at x equals -2, and I'm going to simplify it down. This is our approximation of the value of k at -2.2 using the equation of the tangent line. Okay? Now, final part. Is this greater than or less than the actual value? We have to give a reason. Okay, let's go back to the question stem here. Let's see if we have any clues. What do we know about k? We know it's differentiable for all real numbers. Okay, so that means it's continuous as well. We have particular values of it from the interval from -3 to 3. All right. And look at this last sentence. The second derivative has a property that the k double prime is less than 0. Wait. That means something. What did we learn previously when the second derivative was less than 0? That means k is concave down. Okay, so that means something. What does that mean? If the graph is concave down, then when I go to do my approximation, what does that mean about my approximation? It's going to be above the curve, isn't it? That means any point that I approximate on this tangent line is going to be an overestimate, or in other words, it will be greater than the actual value. So that's what we have to say. What's our reason? Because the function was concave down.